Picture this: the universe, just a fraction of a second old, trembling with the raw energy of its own birth. Space itself stretches and twists like a cosmic drumhead, sending out ripples that will echo for billions of years. These aren't just vibrations, they're the first whispers of reality, gravitational waves carved into the fabric of space-time when the universe was smaller than an atom. And here's the mind-blowing part: we've caught them. Not the echoes themselves, but their fingerprints, hidden in the afterglow of the Big Bang and the dance of distant black holes. But what if these ripples hold secrets we've barely begun to unravel? What if they're clues to realities beyond our own, parallel universes colliding, higher dimensions unraveling, or even the remnants of a cosmos that existed before time began? Strap in, because today we're diving into 30 theories so wild, so revolutionary, they could shatter everything we thought we knew about creation. From quantum foam bubbling at the edge of existence to cosmic strings slicing through dimensions like celestial spaghetti, we're about to explore how the universe's first shivers might rewrite physics itself. And trust me, by the end, you'll never look at the night sky the same way again. Now, let's zoom in on the very first moments of existence, where the tiniest flickers of energy set the stage for everything we see today. Imagine the universe as a seething ocean of quantum foam, a chaotic, bubbling soup where particles pop in and out of existence faster than a blink. This isn't science fiction. It's the bizarre reality dictated by Heisenberg's uncertainty principle, which tells us that even in empty space, energy can't sit still. At scales smaller than an atom, particles and antiparticles constantly collide and vanish, creating microscopic ripples in the fabric of reality. But here's where it gets cosmic. During the universe's explosive infancy, these tiny quantum jitters didn't just fade away, they got stretched. Picture blowing up a balloon with tiny dots on it. As the balloon inflates, those dots grow into vast patterns. That's essentially what happened during cosmic inflation, a period when the universe expanded faster than light itself. Those minuscule quantum fluctuations were magnified to astronomical sizes, becoming the seeds for everything: galaxies, stars, and even the gravitational waves we're hunting today. And the proof, it's written in the cosmic microwave background, the afterglow of the Big Bang. Those faint temperature variations we see, they're the fingerprints of those quantum tremors frozen in time. So every time you look up at the night sky, you're seeing the echoes of a quantum whisper that became a cosmic roar. Now, let's turn our attention to the hard evidence that backs up this mind-bending idea. The Planck satellite, a marvel of modern astronomy, has given us an incredibly detailed map of the cosmic microwave background, the oldest light in the universe. What it reveals is far from uniform. Tiny temperature variations, no larger than a few millionths of a degree, are scattered across the sky like cosmic breadcrumbs. These fluctuations might seem insignificant, but they're actually the smoking gun of those primordial quantum jitters we just talked about. Here's why this matters. The pattern of these hot and cold spots matches exactly what you'd expect if quantum fluctuations were stretched by inflation. Statistically speaking, the data fits the theory with astonishing precision. But science thrives on debate, and not everyone agrees on what these variations mean. Some researchers argue that alternative models like bouncing cosmologies or modified gravity could also produce similar patterns. The key difference: inflation predicts a specific spectrum of fluctuations, one that, so far, the Planck data supports overwhelmingly. Yet the story isn't entirely settled. There are oddities in the data, like the infamous cold spot, where temperatures dip more than expected. Could this be a statistical fluke or a hint of something deeper, like a collision with another universe? For now, the dominant view still points to quantum origins, but these quirks keep scientists digging. Every anomaly is a potential clue, and the cosmic microwave background remains one of our richest windows into the universe's first whispers. Now, let's take a step into one of the most fascinating ideas in modern cosmology, the possibility that our universe wasn't born alone. Imagine a vast cosmic ocean filled with bubbles, each one a universe of its own. This is the multiverse hypothesis, and it suggests that our universe might have formed from a collision between two higher dimensional membranes, or branes for short. Here's how it works. According to string theory, the fundamental building blocks of reality aren't just particles but tiny, vibrating strings. These strings exist in a space with more dimensions than the three we're familiar with. Some theories, like the Randall-Sundrum model, propose that our entire universe could be a three-dimensional brane floating within a higher dimensional space. Now picture two of these branes drifting toward each other and colliding. The energy from that impact could have sparked the Big Bang itself, setting off the expansion of our universe and leaving behind ripples in space-time. What's truly mind-blowing is that such a collision wouldn't just create our universe, it would also generate primordial gravitational waves. Unlike the waves we detect today from black hole mergers, these would carry the imprint of the collision's sheer violence, stretching across the cosmos like echoes of creation. Some models even suggest that these waves could have a distinct signature, one that future detectors like LISA might be able to pick up. Of course, this idea isn't without its critics. Some argue that the math behind brane collisions is still speculative, and others question whether we'll ever find direct evidence. But if we did, it would revolutionize our understanding of reality, proving that our universe is just one bubble in an endless cosmic foam. And that's a thought worth pondering. Now, let's unravel another cosmic mystery, one that involves strange, spaghetti-like threads woven into the very fabric of space-time itself. These are cosmic strings, hypothetical defects that might have formed in the early universe during a dramatic phase transition, moments after the Big Bang. Picture the universe cooling down rapidly, like water freezing into ice. Just as cracks can form in ice, cosmic strings could be the cracks in space-time, remnants of that chaotic shift. These strings aren't ordinary objects. They're unimaginably dense, thinner than an atom but stretching across the cosmos, possibly even longer than galaxies. And here's where it gets wild. When these strings move or vibrate, they could send out gravitational waves, ripples in space-time that echo across the universe. Unlike the waves from black hole mergers, which are brief and violent, cosmic strings might produce a steady hum, a background noise of space-time itself trembling. Scientists have a good idea of what these waves might look like. The ripples from cosmic strings would have a distinct, sharp signature, like sudden kinks or cusps in the string snapping and releasing energy. Detectors like LIGO, which are tuned to catch the violent crashes of black holes, might struggle to spot these subtler signals. That's why cosmic strings remain elusive, hiding in plain sight if they exist at all. But why haven't we found them yet? Part of the challenge is their scale. Cosmic strings could be so massive that their vibrations produce waves with wavelengths too large for current detectors to catch. Or perhaps they're rarer than we thought, making them like needles in a cosmic haystack. Yet, if we ever do detect their whispers, it would be a game-changer, proof that the early universe was a place of extreme energy and wild transformations, leaving behind ghostly threads that still tremble today. So while cosmic strings remain in the realm of theory, they're a tantalizing possibility, one that keeps physicists searching the skies for hints of these ancient vibrations. And who knows, the next big discovery might just be a cosmic string's faint hum, waiting to be heard. Now, let's turn our attention to something even more mind-bending: black holes that don't just sit quietly in space, but actually vanish in a burst of energy. This is the wild world of black hole evaporation, a phenomenon predicted by Stephen Hawking himself. Imagine tiny black holes no bigger than an atom forming in the fiery chaos of the early universe. These aren't the monstrous black holes we see today, but primordial ones born from the extreme densities of the cosmos's first moments. Here's where it gets fascinating. According to Hawking's theory, black holes aren't completely black. They slowly leak energy, emitting what we now call Hawking radiation. Over unimaginably long timescales, this radiation causes the black hole to lose mass and eventually to evaporate entirely. But for those tiny primordial black holes, the process would have been much faster. In the early universe, some of these black holes could have evaporated in a spectacular burst of energy, releasing not just radiation but also gravitational waves, ripples in space-time itself. What makes these ripples special is their frequency. Unlike the deep, rumbling waves from modern black hole mergers, the echoes from evaporating black holes would be high-pitched, almost like a cosmic whistle. That's because smaller black holes evaporate faster, producing waves with much higher frequencies. Detecting these signals would be like tuning into a different channel of the universe, one that reveals a hidden chapter of cosmic history. But why haven't we heard them yet? The challenge lies in their faintness and frequency. Current detectors like LIGO are built to catch the low-frequency rumbles of massive black holes colliding, not the high-pitched whispers of evaporating ones. Future observatories like the proposed Einstein telescope or space-based detectors might finally have the sensitivity to pick up these elusive signals. If we ever do, it would be a revelation proof that the early universe was teeming with these tiny, volatile black holes, each leaving behind a fleeting echo as it disappeared. It's a reminder that even in the darkest corners of space, nothing lasts forever, not even a black hole, and that's a theory worth listening for. Now, let's zoom out from black holes and rewind the cosmic clock even further, back to the universe's first trillionth of a second. This is where Alan Gough's groundbreaking idea, cosmic inflation, takes center stage. Picture the universe expanding faster than the speed of light, stretching from smaller than an atom to the size of a grapefruit in a fraction of a blink. This explosive growth didn't just shape the cosmos, it sent shockwaves through space-time itself, creating what we call inflationary gravitational waves. Here's the key insight: inflation didn't just stretch space, it also amplified tiny quantum jitters into cosmic-scale ripples. Think of it like blowing up a balloon with microscopic wrinkles. Those wrinkles get stretched into vast undulations. These ripples come in two flavors: scalar modes, which affect the density of matter, and tensor modes, which warp space-time directly. It's the tensor modes that leave behind a unique fingerprint, a swirling pattern in the polarization of the cosmic microwave background, the afterglow of the Big Bang. Why does this matter? Detecting these patterns would be like finding the universe's birth certificate. Experiments like BICEP and Keck scan the skies for this telltale swirl, known as B-mode polarization. But it's a needle in a haystack challenge. The signal is incredibly faint, buried under interference from cosmic dust and other astrophysical noise. So far, the hunt has been tantalizing but inconclusive, a reminder that the universe guards its deepest secrets closely. Yet the stakes couldn't be higher. If we ever spot these primordial swirls, it would confirm inflation as the engine of creation and reveal the energy scale at which the universe's expansion went into overdrive. It's a window into physics far beyond the reach of any particle collider, etched into the fabric of space itself. And that's the beauty of inflationary gravitational waves. They're not just echoes of the past. They're a message from the very edge of what we can possibly know. Now, let's take a sharp turn into one of the most mind-bending ideas in modern physics, the holographic principle. Imagine our entire three-dimensional universe, with all its galaxies, stars, and planets, might actually be a projection of information stored on a two-dimensional surface at its boundary. It sounds like science fiction, but this radical idea comes straight from the math of black holes and quantum gravity. Here's how it could connect to those primordial space-time ripples. If the universe is holographic, then everything we experience, including gravity and the fabric of space-time, might just be shadows cast by quantum interactions happening on that distant 2D surface. Think of it like a cosmic movie screen where the real action is happening behind the scenes. Now, here's where it gets wild: quantum entanglement. That spooky connection between particles across vast distances could be the glue holding this holographic universe together. If entangled particles on the boundary encode information about the early universe, then those first gravitational ripples might not have been generated in 3D space at all. Instead, they could be echoes of quantum chaos playing out on the edge of reality. What would that mean for us? If we could decode these holographic imprints, we might uncover secrets about the universe's birth that no telescope or detector can see directly. It's like trying to understand a painting by studying the brushstrokes on the canvas, except the canvas is the edge of existence itself. Some physicists even suggest that future gravitational wave detectors could spot subtle anomalies in the ripple patterns, hints that space-time isn't as three-dimensional as it seems. Until then, the holographic principle remains a tantalizing puzzle, one that blurs the line between science and philosophy and challenges us to rethink where and what reality really is. Now let's shift gears to a shadowy player in the cosmic drama: dark matter. Picture the early universe, a seething, ultra-dense soup where dark matter particles, invisible yet everywhere, constantly crashed into one another. These collisions weren't just quiet bumps in the night. They might have sent violent shudders through space-time itself, leaving behind gravitational ripples we could detect today. Here's the twist: not all dark matter is created equal. Some theories suggest it's cold, slow-moving, and heavy, clumping together like cosmic glue to form the universe's large-scale structure. Others argue it's warm, lighter, and zipping around faster, leaving smoother imprints. The difference matters because cold dark matter would have produced sharper, more localized gravitational waves, while warm dark matter might have generated a subtler, more diffuse ripple pattern. So how do we hunt for these ancient tremors? Future detectors like LISA or the Einstein telescope could tune into frequencies unique to dark matter crashes, filtering them out from the cosmic noise. Another clue might lie in the way galaxies rotate. Dark matter's gravitational fingerprints could hint at whether it was cold or warm when those first ripples formed. But here's the kicker: if dark matter interacts with itself more than we thought, say, through some unknown force, those early particle collisions could have been even more violent, amplifying the ripples. It's like listening for echoes of a long-forgotten thunderstorm, one that shaped the universe in ways we're just beginning to imagine. The mystery isn't just about what dark matter is, but how its hidden dances might have written the first chapters of space-time's story. And if we're right, the next generation of detectors could turn those whispers from the dawn of time into a roar. Now, let's venture into even stranger territory: phantom energy. Imagine a form of dark energy so extreme, it doesn't just push the universe apart, it tears it apart. This isn't your ordinary cosmic expansion. Phantom energy carries negative kinetic energy, meaning the more it stretches space, the stronger its repulsive force becomes. It's like a runaway train with no brakes, accelerating the universe toward a cataclysmic end known as the Big Rip. Here's where things get wild. In the early universe, phantom energy wouldn't just be a future threat, it could have triggered violent instabilities in space-time itself. Picture space as a rubber sheet. Normally, it stretches smoothly, but phantom energy might have made it snap and shudder unpredictably, sending out gravitational ripples like cracks spreading through ice. These tremors wouldn't look like the gentle waves from black hole mergers. They'd be jagged, chaotic, and packed with energy. The Big Rip scenario takes this to the extreme. If phantom energy dominates, it could eventually shred galaxies, planets, even atoms, as space itself rips apart. But long before that final moment, the strain on space-time would have generated gravitational waves with a unique signature, a rising crescendo of frequencies like a scream from the fabric of reality. Detectors like LISA might one day catch these echoes, telling us if phantom energy was there at the dawn of time. What's fascinating is that these ripples could also leave clues in the cosmic microwave background. If phantom energy's tremors twisted space-time in just the right way, they might have imprinted a faint spiral pattern in the afterglow of the Big Bang, a smoking gun for theorists to hunt. So while phantom energy remains speculative, its potential to rewrite the universe's fate and its past makes it one of the most thrilling mysteries in cosmology. Whether it's real or not, the idea alone stretches our imagination to the limit. Now, let's shift gears to a theory that ties the tiniest particles to the grandest cosmic ripples: supersymmetry. Picture the early universe as a boiling cauldron of energy, where particles we've never seen might have danced into existence and vanished in an instant. Supersymmetry, or SUSY for short, proposes that every known particle has a hidden, heavier twin. These shadowy partners could have played a starring role in the universe's first moments. Here's how it works. In the extreme heat of the early cosmos, SUSY particles would have been everywhere, balancing the scales of nature. But as the universe cooled, this perfect symmetry shattered, like ice cracking under pressure, and those heavy twins decayed away. This sudden shift, known as a phase transition, wouldn't have been quiet. Think of it as dropping a boulder into a pond. The collapse of supersymmetry could have sent violent ripples through space-time itself, leaving behind a faint gravitational hum we might still detect today. So why haven't we found these SUSY particles yet? The Large Hadron Collider has hunted for them relentlessly, but so far, no luck. One possibility is they're just too heavy for our current machines to produce. Or maybe they decayed so quickly in the early universe that their traces are vanishingly rare. Some theorists even suggest supersymmetry might work differently than we thought, hidden in extra dimensions or tangled up in other exotic physics. But here's the exciting part. If SUSY is real, those primordial ripples could carry its fingerprints. Future detectors might spot a unique pattern in the gravitational wave background, a whisper from the moment symmetry broke. It's a long shot, but if confirmed, it would rewrite not just particle physics but our entire cosmic origin story. Until then, supersymmetry remains one of the most tantalizing what-ifs in science, a ghostly echo of a universe far stranger than we imagined. Now let's take a step into a radically different vision of reality, one where space-time isn't smooth and continuous, but stitched together from tiny, indivisible pieces. This is the world of loop quantum gravity, or LQG, a theory that reimagines the fabric of the universe as a shimmering web of interconnected atoms of space. Unlike string theory's tiny vibrating strings, LQG suggests that space itself is granular, built from finite loops that weave together to form the cosmos. In the fiery chaos of the early universe, these space-time atoms wouldn't have sat still. Imagine a cosmic drumhead vibrating at the smallest scales possible. Those vibrations, ripples in the very structure of reality, could have left behind a unique gravitational wave signature, one that's entirely different from the predictions of inflation or colliding brain. Instead of a smooth hum, LQG might produce a jagged, quantum-grained whisper in the gravitational wave background, a telltale sign that space itself is pixelated. How does this stack up against string theory? While string theory wraps gravity up with other forces in extra dimensions, loop quantum gravity keeps things closer to home, focusing purely on quantizing space and time within our familiar 4 dimensions. String theory's ripples come from higher dimensional branes or cosmic strings, while LQG's waves emerge from the jittering of space itself. It's a clash of philosophies, one seeking unity, the other embracing discreteness. The real challenge, detecting these quantum ripples, Current observatories like LIGO aren't sensitive to the ultra-high frequencies LQG predicts, but future experiments might just catch a glimpse. If they do, it could mean space isn't the smooth continuum Einstein envisioned, but a dynamic, buzzing lattice at the smallest scales. Until then, loop quantum gravity remains a bold bet on the quantum nature of reality, one that could turn our understanding of space-time inside out. Now let's shift gears to a theory that turns the Big Bang on its head literally. Picture this: instead of a fiery explosion from a single point, our universe might have been born from a cosmic car crash. This is the ekpyrotic universe model, where our reality began when two four-dimensional membranes floating in a higher dimensional space slammed into each other. Think of it like two sheets of paper smacking together in a vast, unseen void. That collision, dubbed the Big Splat, could have sent shockwaves through space-time, creating the primordial ripples we're hunting for today. What makes this different from the classic Big Bang? For starters, no singularity, no infinite density or temperature. Instead, the ekpyrotic model suggests a smoother, more controlled birth. The energy from that collision would have been distributed more evenly, leaving behind a distinct pattern of gravitational waves, one that's less chaotic than the jagged tremors predicted by inflation. If we could detect those ripples, they'd tell us our universe wasn't born from a bang, but from a cosmic fender bender. Here's where it gets wilder. This theory isn't just a one-time event. It's part of a cycle. Those membranes could drift apart, stretch, and then collide again, birthing a new universe each time. That means our cosmos might be one in an endless series, with each collision resetting the clock. The ripples from each splat would carry echoes of previous universes, like cosmic fingerprints layered over and over. The catch, proving it, the gravitational waves from such an event would be faint and stretched across unimaginable scales. But if future detectors like LISA pick up a signal that doesn't match inflation's predictions, we might have to seriously consider that our universe began with a splat, not a bang. Until then, the ekpyrotic model remains a thrilling alternative, challenging us to rethink not just how our universe began, but how it might begin again. Now, let's step into the realm of invisible particles that might hold the key to both dark matter and the universe's earliest ripples. Imagine a ghostly sea of particles so light and elusive, they barely interact with ordinary matter, yet their collective dance could have bent the fabric of space-time itself. These are actions, hypothetical particles born from one of physics' most puzzling problems: why the strong nuclear force seems to ignore certain symmetries in nature. Actions were first dreamed up to solve this mystery, but they quickly became prime suspects in another cosmic whodunit, dark matter. If actions exist, they'd be everywhere, streaming through you right now, their tiny masses adding up to the invisible glue holding galaxies together. But here's where it gets fascinating for our space-time ripples. In the early universe, actions wouldn't just sit still. They'd oscillate like a pendulum swinging back and forth in an invisible field. Those oscillations could have created waves in space-time, subtle tremors imprinted on the universe when it was just a fraction of a second old. The strongest candidate is the QCD action, tied directly to the quirks of quantum chromodynamics. As the universe cooled, this action field would have settled into its lowest energy state, but not without ripples. Think of it like dropping a pebble into a pond. The waves spread outward, but in this case the pond is space-time itself. These ripples would carry a unique signature, different from those left by inflation or colliding brains. The hunt for actions is already underway. Experiments like ADMC's use ultra-sensitive detectors to listen for their faint whispers in magnetic fields. If we catch them, it wouldn't just solve the dark matter puzzle, it could also give us a snapshot of those primordial space-time ripples. Until then, actions remain one of the most elegant two birds, one stone theories in physics, tying together the infinitesimal and the cosmic in one sweeping dance. Now, let's turn our attention to another cosmic player that might have left its mark on the fabric of space-time: neutrinos. These tiny, nearly massless particles are often called the ghosts of the universe because they slip through matter almost unnoticed. But in the first seconds after the Big Bang, they weren't just passive spectators. They were part of an ultra-dense, chaotic sea, and their turbulent motions could have stirred up gravitational waves we're still searching for today. Picture the early universe, a seething hot soup of particles where neutrinos were packed so tightly they couldn't travel freely without bumping into each other. This wasn't a calm ocean, it was a churning storm with neutrinos swirling and colliding in a frenzy. Those violent interactions didn't just generate heat, they might have created ripples in space-time itself. Think of it like dropping a handful of pebbles into a pond, each collision sending out tiny waves but on a cosmic scale. As the universe expanded and cooled, neutrinos eventually broke free, a moment physicists call neutrino decoupling. This was like opening a floodgate suddenly. These particles could stream unimpeded across the cosmos, but their earlier turbulence left behind a faint imprint, a relic background of gravitational waves hiding in the universe's oldest light. Today, we detect neutrinos from the sun and distant supernova, but those primordial neutrinos, they're still out there, a whisper from the universe's first moments. The hunt for these ancient ripples is tricky. Unlike the clear signals from black hole mergers, neutrino-induced waves would be subtle, buried in the noise of other cosmic events. But if we can tease them out, they'd give us a direct window into the universe's infancy, back when even the lightest particles had the power to warp space-time. It's a reminder that sometimes the smallest things leave the biggest echoes. Now, let's shake things up with a bold idea. What if gravity itself isn't quite what Einstein thought? Modified Newtonian dynamics, or MUND, throws a curveball at general relativity by suggesting we might not need dark matter to explain the universe's behavior. Instead, it proposes that gravity works differently on cosmic scales, especially in the faint outskirts of galaxies where stars move faster than they should. But here's the twist: if gravity isn't following Einstein's rules in the early universe, those modifications could have generated space-time ripples all on their own. Take TVS, a tweaked version of MUND that blends it with relativity. This theory imagines gravity as a fluid with extra fields nudging it to behave differently in weak regimes. In the dense, chaotic early universe, these tweaks might have amplified tiny quantum jitters into full-fledged gravitational waves, no dark matter required. Then there's Verland's entropic gravity, an even wilder take. It suggests gravity isn't a fundamental force at all, but an emergent effect like heat rising from the microscopic motion of atoms. If space-time itself is a kind of hologram, its early flickers could have left ripples in ways Einstein never predicted. The beauty of these ideas, they turn the hunt for primordial waves into a test of gravity's true nature. If future detectors catch a ripple pattern that doesn't fit general relativity's mold, it might hint that gravity itself evolved, or that we've been missing a piece of the puzzle all along. Whether MUND, TVS, or entropic gravity wins out, one thing's clear: the universe's first whispers might rewrite the rules of the game. Now, let's turn the tables on black holes and consider their mysterious opposites, white holes. While black holes famously trap everything, even light, white holes are theorized to violently spit out matter and energy, acting like cosmic fountains. Imagine the early universe as a place where these white holes burst into existence, their explosive birth sending shockwaves through space-time. Unlike the slow, steady evaporation of black holes predicted by Hawking, white holes could have unleashed sudden, intense gravitational ripples, leaving behind echoes we might still detect today. What makes this idea even more intriguing is its connection to fast radio bursts, those mysterious flashes of energy from deep space. Some scientists speculate these could be white holes briefly flaring to life, their outbursts matching the kind of signals we'd expect from these theoretical objects. Then there's the quantum bounce model, which suggests the Big Bang itself might have been a white hole explosion, a rebound from a previous universe's collapse. If true, the primordial ripples we're hunting could carry fingerprints of that cataclysmic rebirth. So while white holes remain unproven, they offer a thrilling twist on gravity's extremes. Whether as remnants of a bouncing cosmos or hidden sources of deep space signals, their potential role in shaping the universe's first ripples keeps physicists on the edge of their seats. After all, if white holes are real, they might rewrite not just our understanding of space-time's birth, but its ultimate fate as well. Now, let's rewind the cosmic clock to a time when the universe was just a seething ocean of raw ingredients, a quark-gluon plasma. Picture this, a trillionth of a second after the Big Bang. Space was so unimaginably hot and dense that even protons and neutrons couldn't hold themselves together. Instead, their building blocks quarks and gluons swirled freely in a superheated soup, colliding and rebounding like particles in a cosmic pinball machine. This quark-gluon plasma wasn't just chaotic, it was a stage for dramatic phase transitions. As the universe expanded and cooled, quarks and gluons suddenly froze into protons and neutrons like water turning to ice. But here's the twist. That phase change likely sent shockwaves rippling through the plasma, distortions so powerful they could have imprinted gravitational waves onto the fabric of space-time itself. Scientists have actually recreated tiny slices of this primordial soup in labs like the relativistic heavy ion collider, smashing gold ions together at nearly light speed to briefly resurrect quark-gluon plasma. What they've found is astonishing. The plasma behaves like a perfect, frictionless liquid, with shockwaves propagating in ways that hint at how those early universe tremors might have formed. If these experiments are any guide, the quark-gluon era didn't just shape matter. It could have left behind faint gravitational echoes, whispers of a time before atoms even existed. So while we can't travel back to witness that seething cosmic dawn, colliders give us a front-row seat to its physics. And if future detectors catch ripples from this violent infancy, they'll be decoding a message from the universe's very first moments written in the language of quarks, gluons, and the space-time wrinkles they left behind. Now let's stretch our imaginations beyond the familiar 3 dimensions of space and one of time. What if the universe's first ripples weren't just born from events in our visible reality, but from hidden dimensions unraveling? Picture this. The early cosmos might have been like a tightly wound ball of yarn, with 6 or 7 extra dimensions curled up into microscopic knots, too tiny for us to perceive. These compactified dimensions, described by string theory's intricate Calabi-Yau shapes, could have suddenly unfurled during the universe's explosive infancy, releasing pent-up gravitational energy like a coiled spring snapping open. The physics gets wild here. As these extra dimensions expanded, they'd have vibrated at specific frequencies called Kaluza-Klein resonances, ripples in the very geometry of higher dimensional space. Some theories suggest these vibrations could have imprinted unique patterns onto our 4-dimensional space-time, leaving behind gravitational waves with telltale signatures. Imagine tuning a cosmic radio. If future detectors like LISA pick up faint, high-pitched chirps unlike any black hole merger, they might be hearing the echoes of dimensions we've never seen directly. Here's the kicker. This idea isn't pure speculation. Particle colliders have hunted for Kaluza-Klein particles, higher dimensional ghosts that would appear as heavy duplicates of known particles. While none have been found yet, the math is tantalizing. If extra dimensions did shake loose gravitational waves in the early universe, their discovery would rewrite not just cosmology but the very nature of reality. We'd finally have proof that the cosmos is far grander and stranger than the dimensions we call home. Now, let's step into a realm where time itself behaves in ways that defy our everyday intuition. Imagine a structure that never settles into equilibrium, a pattern that repeats endlessly without energy loss. This is the bizarre world of time crystals. Unlike ordinary crystals, which have atoms arranged in repeating spatial patterns, Time crystals exhibit a repeating pattern in time, ticking like a perpetual clock even in their lowest energy state. In the early universe, these exotic structures might have formed as quantum fluctuations froze into place, creating ripples in space-time simply by their relentless, rhythmic motion. The key here is broken time symmetry. Normally, the laws of physics don't care if time runs forward or backward, but time crystals break this symmetry, locking into a cycle that prefers one direction. This violation could have left faint but detectable imprints in gravitational waves, like cosmic fingerprints of a universe that never quite stopped moving. What's truly mind-bending is that time crystals aren't just theoretical. They've been created in labs using chains of ions or superconducting qubits, where they pulse indefinitely without energy input. If similar structures existed in the primordial cosmos, their oscillations might have amplified quantum jitters into full-fledged space-time ripples. Future detectors could hunt for these signals, searching for patterns that repeat with eerie precision, a ghostly echo of a universe that never stopped dancing. Now let's venture into one of the most unsettling ideas in modern physics, the Boltzmann brane paradox. Picture this: in the vast, chaotic sea of quantum fluctuations that filled the early universe, random chance could have momentarily assembled a fully self-aware brain, complete with false memories of an entire universe that never actually existed. This bizarre thought experiment forces us to confront a chilling question: how do we know we're not just fleeting illusions conjured up by quantum chaos? The paradox gets its name from Ludwig Boltzmann, the physicist who first grappled with the idea that entropy could create order by sheer accident. In the primordial universe, where energy and particles were wildly colliding, quantum jitters might have briefly forged conscious observers, Boltzmann brains whose very act of perceiving reality could have warped space-time itself. Imagine a ripple in the cosmic fabric, not from a collapsing star or colliding black holes, but from a disembodied mind blinking into existence and questioning its own reality. Here's where it gets even stranger. If these phantom observers were more likely to emerge than entire, stable universes, then statistically, you're far more likely to be a Boltzmann brain than a real person in a real cosmos. That's the philosophical gut punch. This theory doesn't just challenge our understanding of space-time ripples, it threatens the foundation of how we trust reality at all. Yet there's a silver lining. If future gravitational wave detectors pick up anomalies, ripples with no obvious cosmic source, they might be echoes of these quantum apparitions. Or perhaps proof that the universe prefers creating lasting structures over fleeting hallucinations. Either way, the Boltzmann brain paradox reminds us that the deepest mysteries of space-time aren't just about physics, they're about the very nature of existence itself. Now let's shift gears to a theory that twists gravity itself into something even Einstein might not recognize: Chern-Simons gravity. This isn't your everyday tweak to general relativity. Instead, it's a radical reimagining where the very fabric of space-time gets a strange, asymmetric twist. Here's the wild part. In this model, gravity doesn't play fair between left and right. Certain gravitational waves, ripples in space-time, get a turbo boost depending on their handedness, a phenomenon called parity violation. Think of it like a cosmic seesaw. Normally, gravity treats left-handed and right-handed waves equally, but Chern-Simons gravity tips the scales. Some ripples become louder while others fade into the background. This isn't just theoretical gymnastics. If true, it could explain why we've detected some gravitational waves with unexpected polarizations, like a fingerprint of this exotic physics etched into the universe's earliest moments. And here's where it gets exciting for future discoveries. The upcoming LISA mission, a space-based gravitational wave detector, could be the key to testing this idea. LISA precision might catch the subtle imprints of Chern-Simons gravity, those amplified ripples hidden in the faint whispers from colliding black holes or neutron stars. If it does, we'd be staring at proof that gravity itself has a hidden asymmetry, a fundamental lopsidedness woven into the laws of physics. So why does this matter? Because Chern-Simons gravity isn't just about rewriting textbooks. It's a clue that the universe's first ripples might carry secrets about dimensions we've yet to comprehend, or even flaws in our understanding of reality itself. One thing's certain: the deeper we listen to space-time's echoes, the stranger the cosmos becomes. Now, let's turn our attention to one of the most fiery debates in modern physics: black hole firewalls and the echoes they might have left in the fabric of space-time. Picture this: as a black hole forms, some theories suggest its event horizon isn't just a quiet boundary but a raging inferno, a firewall of intense energy. If true, the birth of these cosmic monsters could have sent violent ripples cascading through the universe, gravitational waves carrying the signature of their explosive origins. But here's where things get tricky. Not everyone agrees firewalls exist. Stephen Hawking proposed an alternative called the soft hair theory, where black holes leave behind subtle, almost ghostly imprints, gentle distortions in space-time rather than fiery explosions. The difference is stark. Firewalls scream their presence while soft hair whispers. So which one leaves a trace in the universe's earliest ripples? Detecting these signals isn't easy. Firewall echoes would be sharp, sudden bursts like a cosmic alarm bell, while soft hair would produce smoother, more elusive waves. Current detectors like LIGO might struggle to spot the difference, but future upgrades or space-based observatories could have the sensitivity to settle the debate. Imagine the implications. If we find evidence of firewall echoes, it would mean black holes are far more violent than we thought, rewriting our understanding of their birth and death. This isn't just academic squabbling. The answer could reveal whether the universe's first ripples were forged in fire or shaped by something far more subtle, a question that cuts to the heart of how space-time itself behaves under extreme conditions. One thing's certain: the deeper we probe these mysteries, the more surprises await. Now, let's venture into an even more mind-bending possibility. What if neutron stars existed before the Big Bang itself? Imagine a cosmic soup so dense and extreme that it birthed neutron star-like objects in the universe's earliest moments. These ultra-compact remnants, packing the mass of a star into the size of a city, could have collided and merged, sending powerful ripples through the fabric of space-time long before the first galaxies even formed. This idea ties into the Planck star hypothesis, where the core of a black hole isn't a singularity but a tiny, ultra-dense object like a neutron star pushed to its absolute limit. If such objects existed in the primordial universe, their mergers would have been cataclysmic, leaving behind gravitational wave signatures unlike anything we see today. The key difference: these ripples would carry the imprint of a universe far hotter and denser than anything we've ever observed. Detecting these ancient echoes would be like finding fossils from a time before time. Current observatories might not be sensitive enough to pick up such faint, high-frequency signals, but future detectors could tune into this primordial symphony. If successful, it would rewrite our understanding of the universe's birth, suggesting that the cosmos we know emerged from something even stranger, a seething ocean of neutron matter, churning with collisions that shaped the very first ripples in space-time. The implications are staggering. It would mean the universe's infancy was far more violent and exotic than we ever imagined, with neutron stars acting as cosmic sculptors, carving their mark into the fabric of reality itself. And if Planck stars are real, their remnants might still linger, hidden in the heart of black holes, waiting to reveal their secrets. One thing's clear: the deeper we dig into the universe's past, the more surprises we uncover. Now let's take a sharp turn into the bizarre world of quantum connections, where wormholes and entanglement might be two sides of the same cosmic coin. Picture this: what if the strange, instantaneous link between entangled particles is actually a tiny, hidden wormhole threading through space-time? This wild idea, known as ER equals EPR, suggests that every time particles become entangled, a microscopic wormhole forms between them, bridging the gap no matter how far apart they are. When these quantum wormholes collapse, snapping shut like a rubber band stretched too far, they could send out ripples in space-time, faint echoes of their brief existence. It's a bit like quantum teleportation, where information jumps from one place to another without traveling the distance in between. If wormholes really are the secret machinery behind entanglement, their sudden disappearance might leave gravitational fingerprints, a subtle tremor in the cosmic background. The implications are dizzying. It would mean that the universe's most fundamental connections, those spooky quantum links Einstein famously doubted, are literally woven into the fabric of space itself. Detecting these ripples would be like catching whispers from a hidden dimension, where the rules of distance and separation don't apply. Future experiments might one day spot these signals, revealing that the universe's first tremors weren't just random quantum noise, but the aftershocks of countless wormholes flickering in and out of existence. And here's the kicker. If this theory holds, it could mean that space-time isn't just a static stage for particles to move on. It's a dynamic, living thing, constantly being stitched together by these quantum threads. The ripples we're hunting might not just be remnants of the Big Bang, but clues to a deeper, weirder truth, that the universe is held together by an invisible web of wormholes, humming with gravitational echoes of their own creation. Now, let's step into one of the most unsettling possibilities in physics, a cosmic doomsday scenario hiding in the very fabric of reality. Imagine the universe as a valley with the Higgs field, the invisible energy field that gives particles their mass sitting comfortably at the bottom. But what if this valley isn't the lowest point? What if there's a deeper, more stable state lurking beneath, and our universe is just teetering on the edge? This is the nightmare of vacuum decay. If the Higgs field were to suddenly tunnel into that lower energy state, it would unleash a bubble of true vacuum expanding at the speed of light. Inside this bubble, the laws of physics as we know them would rewrite themselves. Atoms could unravel, forces might cease to exist, and the universe as we know it would vanish in a catastrophic wave. And here's the chilling part. It could have already happened in the early universe, with these bubbles colliding and sending violent shockwaves rippling through space-time. The gravitational waves from such an event wouldn't just be faint whispers, they'd be deafening crashes. Distortions so massive they'd dwarf anything from black hole mergers. If we ever detect these primordial ripples, they could be the smoking gun of a universe that narrowly escaped annihilation, or worse, a sign that we're still sitting on a ticking time bomb. Some theories even suggest that the Higgs field might be just stable enough to avoid decay for now. But in the chaos of the early universe, where energies were unimaginably high, vacuum decay could have been triggered repeatedly, leaving behind a gravitational wave background that's more like a cosmic minefield. Future detectors might one day pick up these echoes, revealing whether we're living in a universe that's eternally safe, or one that's perpetually one quantum fluctuation away from oblivion. And if that's not enough to keep you up at night, consider this. If vacuum decay happened once, it could happen again. The ripples we're searching for might not just be relics of the past, they could be warnings from the future. Now let's spin the cosmic wheel and explore a universe that never sits still. Gödel's rotating universe. Picture the entire cosmos as a vast, swirling vortex, where space-time itself is dragged along by the motion, like water circling a drain. This isn't just a thought experiment, it's an exact solution to Einstein's equations of general relativity, dreamed up by the brilliant mathematician Kurt Gödel. In his model, the universe isn't just expanding, it's rotating, twisting the fabric of reality into strange, closed loops where time could, in theory, bend back on itself. But here's the mind-bending question. Could this universal spin have left behind ripples in space-time? Just as a spinning black hole drags space-time around it, a phenomenon called frame-dragging. Gödel's universe might have imprinted its rotation onto the early cosmos, creating gravitational waves that still echo today. These wouldn't be the chaotic crashes of colliding bubbles or black holes, but something far subtler, a faint, swirling hum woven into the background of the universe. Detecting such ripples would be like listening for the whisper of a cosmic top spinning since the dawn of time. Current observatories might not be sensitive enough to pick up this signal, but future missions like the Laser Interferometer Space Antenna could be tuned to hunt for these ghostly rotations. If found, they'd offer proof that the universe itself once turned like a giant wheel, and that Einstein's equations hold even in the most bizarre corners of reality. And there's a deeper mystery here. If the universe did rotate even slightly, it would challenge our assumptions about cosmic isotropy, the idea that the cosmos looks the same in all directions. A spinning universe would have a preferred axis, a cosmic North Star pointing the way to its primordial motion. So far, observations suggest our universe is remarkably uniform, but Gödel's solution reminds us that the rules of gravity allow for far stranger possibilities. Maybe the ripples we're searching for aren't just remnants of violence, but fossils of a universe that never stopped dancing. Now, let's step into a universe where reality itself might be pixelated, where the very fabric of space-time has a built-in limit to how precisely it can be measured. This is the wild idea behind holographic noise, a theory championed by physicist Craig Hogan. Imagine space-time not as perfectly smooth but as a kind of cosmic static, a fuzziness at the smallest scales, like an old television screen tuned between channels. According to Hogan, this quantum jitter isn't just background, it's a fundamental feature of the universe, a noise floor created by the limits of how much information space-time can hold. So how does this connect to gravitational waves? If space-time has this inherent fuzziness, then every ripple passing through it, every gravitational wave from the dawn of time, would carry a tiny imprint of that noise. It's like trying to listen to a whisper in a room filled with static. The question is, could our detectors, like LIGO or future observatories, pick out these subtle distortions from the cosmic hum? Some researchers argue that holographic noise would show up as a specific pattern in gravitational wave data, a telltale sign that space-time itself is granular at the quantum level. But here's the catch: this noise would be incredibly faint, buried under other cosmic signals and even the limitations of our own technology. Detecting it would require instruments far more sensitive than what we have today, pushing the boundaries of quantum measurement itself. And if we did find it, the implications would be staggering. It could mean that the universe operates like a hologram, where three-dimensional reality is actually encoded on a two-dimensional surface, with space-time emerging from something far stranger. For now, holographic noise remains a tantalizing what-if, a theory that dances on the edge of what we can observe. But as detectors grow more advanced, we might finally answer whether the universe's ripples are riding on a sea of quantum static, or if space-time is smoother than we ever imagined. Either way, the hunt for this noise could rewrite our understanding of reality itself. Now, let's take a journey into one of the most mind-bending ideas in modern cosmology, a theory that suggests the universe might not have a true beginning or end, but instead cycles endlessly through rebirth. This is the heart of Sir Roger Penrose's conformal cyclic cosmology, or CCC for short. Picture this: what if our Big Bang wasn't the first, but simply the latest in an infinite series of universes, each leaving faint echoes in the next? According to Penrose, the far future of our universe, a cold, empty expanse where black holes have evaporated and particles have decayed, would eventually become indistinguishable from the high-energy singularity of a new Big Bang. In this model, the boundary between one universe and the next isn't a wall but a transformation, a cosmic reset where the laws of physics reconfigure themselves. And here's where it gets wild. Gravitational waves from the previous universe could, in theory, survive this transition, imprinting themselves onto the newborn cosmos like cosmic fingerprints. So how would we spot these ancient ripples? The key might lie in the cosmic microwave background, specifically in a pattern called B-mode polarization. These are swirls in the leftover light from the Big Bang, and while some are caused by gravitational lensing, others could be signatures of primordial gravitational waves. Penrose and his collaborators argue that certain anomalous hotspots in the CMB, like the so-called Hawking points, might actually be remnants of supermassive black holes from a prior universe, their final gravitational waves etched into the fabric of the new one. Of course, not everyone's convinced. Critics point out that these patterns could have more mundane explanations, like statistical flukes or dust in our own galaxy. And the math behind CCC is notoriously complex, blending general relativity with abstract geometry in ways that even many physicists find hard to parse. But if Penrose is right, the implications are staggering. It would mean that time is far stranger than we thought, with each universe inheriting whispers of its predecessor, a cosmic memory written in space-time itself. For now, CCC remains a bold hypothesis, one that challenges our deepest assumptions about beginnings and endings. But as we refine our measurements of the CMB and push gravitational wave detectors to new sensitivities, we might just find evidence that the universe has been here before, and that its oldest ripples are still echoing through the void. Now let's shift gears and consider something truly out of the box. What if the universe itself is a simulation? This isn't just science fiction. Some physicists and philosophers seriously entertain the idea that our reality might be an advanced computational construct. And if that's the case, those primordial space-time ripples we've been detecting, they could be nothing more than glitches in the code. Imagine a universe running on some cosmic computer. Even the most sophisticated simulations have limits: processing power, memory constraints, and tiny imperfections in the underlying code. These limitations might leave subtle traces, like a faint grid-like structure in the fabric of space-time known as lattice artifacts. If the universe is pixelated at the smallest scales, gravitational waves could carry the signature of that digital framework, revealing the resolution of our simulated reality. But how would we spot these glitches? One clue might come from anomalies in high-energy physics or the behavior of particles at extreme scales. If space-time has a built-in pixel size, certain phenomena like the way light travels or how black holes evaporate might deviate ever so slightly from what Einstein's equations predict. Some researchers even propose that if the simulation has a finite processing speed, the speed of light might not be perfectly constant but could fluctuate in ways we haven't yet detected. Of course, this idea isn't without its critics. Many argue that the simulation hypothesis is untestable, or worse, that it's just a modern twist on age-old philosophical questions about the nature of reality. And even if we are in a simulation, the creators might have designed it so flawlessly that we'd never find the seams. Still, the possibility is tantalizing. If primordial ripples turn out to bear the marks of computational limits, it could be the closest thing we ever get to a system error message from the cosmos. Whether you find the idea thrilling or far-fetched, it forces us to ask deeper questions. If the universe is a simulation, what does that say about the nature of existence? And if those ripples are glitches, well, who's running the program? For now, it's a playful but profound theory, one that blurs the line between physics and philosophy. And as we push the boundaries of detection, we might just find that the universe has been hiding its source code all along. Now, let's take a step into the shadowy side of the cosmos, where dark energy and dark matter might not be separate entities at all, but a single mysterious fluid. Picture this, a vast, swirling ocean of dark fluid where turbulent vortices twist and churn, sending ripples through the fabric of space-time itself. This idea flips the script on how we think about the universe's hidden components. Instead of treating dark matter and dark energy as distinct phenomena, some theorists propose they're two faces of the same cosmic substance, a dark fluid with bizarre properties. When this fluid moves, it doesn't flow smoothly. Like water spiraling down a drain, it creates whirlpools of energy, and those vortices could have generated the primordial gravitational waves we're searching for today. What makes this theory even more intriguing is its connection to superfluid vacuum theories. In quantum physics, superfluids are liquids that flow without any friction, and some researchers suggest the vacuum of space itself might behave like one. If the dark fluid shares these properties, its vortices wouldn't just fade away, they'd leave lasting imprints, like cosmic fingerprints etched into the early universe. But how do we test such a wild idea? One clue might lie in the way these vortices interact with ordinary matter. If dark fluid vortices distorted space-time in unique ways, they could have subtly influenced the formation of galaxies, leaving behind patterns we might spot in telescope data. Another possibility is that these ripples would have a distinct frequency signature, different from those predicted by other theories, giving future detectors like LISA a specific target to hunt for. Of course, not everyone is convinced. Critics argue that the dark fluid model adds unnecessary complexity when simpler explanations might suffice. Yet, if evidence ever points to these turbulent vortices, it could solve two cosmic mysteries at once, unifying dark matter and dark energy while explaining the origins of space-time's earliest ripples. Whether this theory holds up or not, it reminds us just how fluid our understanding of the universe really is. The cosmos might not be built from separate, static ingredients, but from dynamic, interconnected phenomena where even the darkest corners could be swirling with hidden motion. And if we listen closely to the whispers of gravitational waves, we might just catch the echoes of that ancient turbulence. Now, let's shift our gaze to the quantum realm, where the very act of observation might have shaped the universe's first ripples. Imagine the cosmos in its infancy, a seething quantum soup where countless possibilities flickered in and out of existence. But how did certain quantum states survive while others vanished? Enter quantum Darwinism, a radical idea suggesting that the universe itself played the role of a cosmic selector, amplifying some quantum fluctuations into the space-time ripples we detect today. Here's how it works. In the quantum world, particles exist in a haze of probabilities until they're observed, collapsing into a definite state. Quantum Darwinism proposes that in the early universe, certain states were selected because they could leave more robust imprints on their environment, like footprints in wet cement. These surviving states didn't just linger, they grew exponentially during inflation, stretching microscopic quantum jitters into planet-sized gravitational waves. What's even wilder is how this ties to emergent gravity. Some theories suggest gravity isn't a fundamental force but arises from the way quantum information spreads and interacts, like the way temperature emerges from countless atoms jostling. If that's true, then the ripples we see today might not just be echoes of the early universe's chaos, but a literal snapshot of how gravity itself was born from quantum selection. But the real twist: observer effects. In quantum mechanics, the act of measurement changes the system being observed. If the infant universe was a quantum system, could its own evolution have been shaped by an implicit observation? Not by conscious beings, but by the environment's natural interactions. This would mean the ripples we detect aren't just random noise, but the universe's way of leaving a record of its own quantum decisions. Skeptics argue this veers into philosophy, but proponents point to subtle patterns in the cosmic microwave background that could hint at quantum Darwinism at work. Future detectors might even spot telltale asymmetries in gravitational wave frequencies, a fingerprint of this primordial selection process. Whether this theory holds water or not, it forces us to confront a profound question. Did the universe shape its own destiny through quantum choices? If so, those first ripples aren't just relics of the past. They're the cosmic equivalent of a birth certificate, stamped by the laws of quantum survival. And as we decode their secrets, we might finally understand how randomness gave way to the ordered cosmos we call home. Now, let's take a step back and marvel at the cosmic tapestry we've unraveled. From colliding bubble universes to the holographic echoes of a two-dimensional reality, these theories stretch the limits of our imagination. Some suggest space-time ripples were born from quantum foam, while others argue they're artifacts of a universe-scale simulation. Each idea, no matter how wild, offers a unique lens to peer into the dawn of time. The beauty of these theories lies in their testability. Upcoming missions like the Laser Interferometer Space Antenna and the Einstein Telescope will hunt for the faintest whispers of gravitational waves, potentially confirming or dismantling these bold ideas. Will they find evidence of cosmic strings vibrating like guitar strings, or perhaps traces of primordial black holes evaporating into the void? The answers could rewrite physics itself. But here's the most thrilling part: some ripples in space-time might defy all our predictions. The universe has a habit of surprising us, revealing phenomena we never thought to imagine. What if the first gravitational waves carry signatures of dimensions we can't perceive, or echoes of a time before the Big Bang? The deeper we listen, the more questions arise. So as we close this journey, don't just ponder the theories we've explored. Ask yourself, what cosmic secrets remain hidden in the ripples? The universe is still speaking, its oldest stories encoded in vibrations across the fabric of reality. And if you're as fascinated by these mysteries as we are, hit that subscribe button and ring the notification bell. Together, let's keep unraveling the cosmos, one ripple at a